Okay, we'll just recap part D of this. So for time greater than 0, there's a point on the curve where the line tangent to the curve has a slope of 2. At what time t is the object at this point? Well, the first thing that this brings in is that we're looking for the slope of the curve. We're looking for the slope of a parametric curve, and so that is dy dx is equal to dy dt over dx dt, as I have there. And so we brought in our calculator and we set up these two functions, y2 over y1. So what y2 is dy dt, and y1 is dx dt. So we have dy dt over dx dt, and we want to find out where that slope is equal to 2. So we also set up the curve y is equal to 2. Then when we go out and graph these functions, zoom, standard, and graph those two functions, we can see that they do intersect. And if I were to go in and find the intersection point, the first curve is there, the second curve is there. I'm going to move close to the point of intersection and guess, and it's at 1.3576631, etc. Alright, notice that value is stored in x, and so if I went out from here now, second quit, and I said x store in A, that value is now stored in A. So I wrote down here that this occurs, that the slope of the curve is 2 when time is equal to 1.3577, etc. And rounding that to 3 places might be 1.358. Alright, and then we're looking to find the acceleration vector at that particular point. So to find the acceleration vector, well, we need the derivative of dx dt at that particular point in time. And we need the derivative of dy dt at that particular point in time. So I go back to my functions, and I'm going to turn on my dx dt and my dy dt, and I'm going to turn off the other two functions that I have down here, and zoom, standard, and I have my two functions there. Now what I need are not the values of these functions at 1.357, etc. That would give me the velocity vector. What I need, though, is the derivatives or the slopes of those curves at that point in time, and that will give me the acceleration vector. So what I'm going to use is not value here, but I'm going to use the derivative. And you can see that I'm on the arctan 1 plus arctan of x over 1 plus x, and so I want to find that at time t equals a, since I already have that stored, and it gives it to me as 0.135, and that is my x coordinate. Now all I need to do is move up, and now I'm on the dx dt curve, and actually I'm already there. It's at 1.04. But what I want to find now, again, is second calc. I'm looking for the derivative of that curve at time, x equals a, and I'm still on that other curve here. So I need to go back to second calc dy dx. Now I'm going to move up to that curve and put in x equals a, and that gives me 0.955. So you have to be really careful with that. If you notice, what happened there was that I had selected the dy dt curve, and then I started to find the derivative of that curve, and it jumped me down back to the dx dt curve. So you actually have to start the derivative and then position yourself on the curve that you're looking for and find it. Now fortunately we knew that it was the wrong answer because it was the same thing we got for dx dt. And so that's all we have for that, and that wraps up this problem as well.